Hello students, welcome to First PU video classes organized by Mysore District PU Chemistry Lecturers Forum. Do subscribe to our YouTube channel My PU Chemistry to watch more videos. I am Nandita N. Nair from Gopal Swami PU College, Mysore. So today I shall be handling the chapter Chemical Bonding. Now under chemical bonding there are three very important theories, okay, out of which I shall be handling two theories today. We will start with VSEPR theory. Now what does VSEPR stand for? Valence, shell, electron, pair, repulsion theory. From the name itself, the actual theory itself comes into picture, okay. So valence, shell, electron, pair, repulsion theory. So in very simple words I will put it across. In the valence shell of the central atom there will be electron pairs. These electron pairs could be bond pairs, they could be lone pairs also. Now you should remember bond pairs are the electrons which are involved in bonding, whereas lone pairs are the electrons which have not been used for bonding, okay. So in the valence shell there could be electron pairs, those could be bond pairs as well as lone pairs. Now these electron pairs will repel each other obviously because they are of the same charge. Due to repulsion the molecule will become unstable. If the molecule has to become stable, the repulsions has to be minimized. The repulsion to be minimized, they should be, that is the electron pair should be kept maximum distance apart. This is the whole concept behind VSEPR theory, okay. So I will explain point wise again. So VSEPR theory was proposed by Sidgwick and Powell in the year 1940. Now, as I said, the shape of a molecule depends on the electron pairs around the central atom. So, there will be a central atom and that central atom will have electron pairs in its valence shell. These electron pairs repel one another, okay. Now, if you need the molecule to be stable or for the stability of the molecule, these electron pairs must occupy such positions in space so as to minimize the repulsions. So when I say minimize the repulsions, that means they have to be kept maximum distance apart. Now this results in a specific geometry, okay. Now while considering the repulsions, one more very important point that has to be noted is that lone pair repulsion is more or stronger than lone pair bond pair repulsion, and that's stronger than bond pair repulsion. So while we arrange the electron pairs, care should be taken that the lone pair repulsion must be placed maximum distance apart in comparison to lone pair bond pair repulsions and bond pair repulsions, okay. So these are the different postulates about the VSEPR theory. Now just a few things I would like to explain. Why is it that lone pair repulsion is so much greater than the other two? Now it's very simple. The lone pair is localized on the central atom alone, whereas the bond pair is between two atoms. So the lone pair is on the central atom itself, therefore the repulsion between lone pairs will be more than with a bond pair or between two bond pairs. So lone pair repulsion is the one that you have to keep as far apart as possible, okay. So these are the postulates of VSEPR theory. Now one more thing I would like you all to remember, two terms I would like to introduce. When you do not have any lone pairs, where there are no lone pairs in the molecule, you may consider that as regular geometry. So without lone pairs, meaning to say only bond pairs, we can consider that geometry as regular geometry, whereas if there are lone pairs along with the bond pairs, that geometry we are going to call as distorted geometry. Why? Because when lone pair is there, the bond angles will get distorted and we can refer to that geometry as distorted geometry. So having gone through the points of VSEPR, now the next thing for us is to have the entire chart about different compounds and what their geometry or shapes will be like, okay. Now, considering the different examples that we can use it for VSEPR theory, let me start with the simplest formula. I am writing AB2. So, when I write AB2, understand A is the central atom and there are 2 bond pairs. Okay? So, 2 bond pairs, there are no lone pairs, which means the total electron pairs is 2. The total number of electron pairs is 2. So, if you have the central atom and you want to keep the bond pairs as far apart as possible, which means they can be kept 180 degrees apart. So, this bond angle will be 180 degrees and the geometry would be linear. The geometry would be linear. For examples, we can take carbon dioxide or beryllium chloride. You can take carbon dioxide or beryllium chloride. So, this is for the formula AB2. Now, the second example that I would like to take is AB3. The second example that we are going for is AB3. You have 3 bond pairs and 0 lone pairs and you have a total number of electron pairs as 3. Again, central atom of course in the center and you have 3 bonded atoms or 3 bond pairs, right. So, they are at an angle of 120 degrees apart, and if I outline like this, then this geometry is called trigonal planar. So, you have trigonal planar. It's a planar molecule. It's like on a single plane. Okay. So, you have a planar molecule. The example that we can quote for this is BF3 or AlCl3. BF3 or AlCl3. Now I will put a star. I will explain what that star is later. Okay. So, these 2 examples I am putting a star. You have to remember what the star is for. I will explain that later. Now I am moving on to a third situation. Okay. In the third situation, I am writing it as AB2L. So, which means there are 2 bond pairs, 1 lone pair on the central atom and you are having total 3. Total 3. I am going to make a change here itself so that you will understand. The geometry remains trigonal planar. Now, when I say geometry remains trigonal planar, what I mean to say is the orientation of the atoms. I am going to take this off and I am going to tell you that the orientation of the atoms remains as a triangle. So, instead of having a bond pair, you are having a lone pair here. So, the shape will not come, but there is a lone pair. So, the 3 electron pairs are still arranged in the form of a trigonal planar, meaning the geometry of the molecule is trigonal planar, but the shape of the molecule will be bent because there is no atom on the top. So, the shape of the molecule becomes bent. So, this is what you need to understand, that whenever lone pairs come into the formula, the shape and the geometry will be different. In the previous 2 examples, I did not specify any shape, but from now on, whenever there is a lone pair or 1 or more lone pairs, the geometry and the shape of the molecule is going to change. So, the geometry is still trigonal planar because the orientation of the electron pairs are still like a triangle, but the shape has become bent. The shape has become bent also. Now, there is lone pair bond pair repulsion. Now, which is more dangerous? Lone pair bond pair repulsion is more dangerous. Therefore, the bond pairs which were like this will come a little closer. For what reason? Because compared to lone pair bond pair repulsion repulsion is not so bad. As a result of which, this bond angle will be less than 120 degrees because the bond pairs come a little closer. So, the bond pair or the bond angle here will be less than 120 degrees to avoid lone pair bond pair repulsion. To keep them far apart, the bond pairs will come closer. Okay. And the examples that I can quote for this, of course I am removing these 2 examples here. The examples I can quote is SO2 and O3. SO2 and O3. So, these are the examples for AB2L. Okay. The next formula that we are going to look at is AB4. I am going to put a star again. I think by now you should have got an idea that I am putting a star for those geometries which do not have lone pair. And what was the name that I already said for such geometries? I said they are regular geometries. So that star indicates regular geometry. Okay. Now, how many bond pairs? You can see there are 4 bond pairs and there are 0 lone pairs and the total is 4. Now, when you have 4 bonds, I am going to place it like this. I am going to place it like this and you have a bond on top. So, if you outline like this, you have what is called a tetrahedral geometry. So, this is a tetrahedral geometry and the bond angle is 109 degree 28 minutes. Many books you might find it as 109.5 degrees, that is also fine, but exact value to be correct, to be very clear, it is 109 degree 28 minutes. Okay. Now, the example that you have for this is methane or maybe CCl4, etc. So, you have methane or CCl4 as examples for a tetrahedral geometry. How many bond pairs? There are 4 bond pairs. There are no lone pairs. So, this is a regular geometry and the geometry that you get is a tetrahedral geometry. Okay. Now, I am going to show you the distortions that can happen to this geometry. Okay. So, next one that I am going for is AB3L. Now, AB3L. Remember, the total number is still 4. The total number is still 4. The total number of electron pairs is still 4. Now, you have 3 bond pairs and 1 lone pair. Now, when you have 3 bond pairs and 1 lone pair, I am going to change the structure a little for you. So, let us see what happens now. So, here again you have A in the center, you have B, another B and a B, but you have in the 4th position that bond has been replaced by a lone pair. When that happens, now the shape is like a pyramid. The shape is like a pyramid. You do not have the atom on the top. The geometry is still tetrahedral, mind that. So, geometry is still tetrahedral. Why? Because the orientation of the electron pairs is still in the form of a tetrahedron. So, the geometry is still tetrahedral, but now what happens to the shape? There is no top atom. There is no top atom. So, the shape becomes pyramidal. The shape becomes pyramidal. So, the geometry is tetrahedral, but the shape of the molecule turns out to be pyramidal. Okay. One example that I will quote for this is NH3. Now, again, because of the lone pair, the bond pairs will come closer. We already saw that in the previous example. To avoid lone pair bond pair repulsions, the bond pairs come closer, which means the bond angle will be less than 109 degree 28 minutes. For ammonia specifically, I would like you to remember that the bond angle is 107 degree. I do not mean that all pyramidal geometry or all pyramidal shapes have 107 degree. No, I mean ammonia is having a bond angle of 107 degree. What is the reason for the decrease in bond angle? To avoid lone pair bond pair repulsion, the bond pairs will come closer. Okay. So, this is your AB3L. Now, moving on, one more under the same category, I have AB2L2, AB2L2, which means total is still 4, 2 bond pairs and 2 lone pairs. 2 bond pairs and 2 lone pairs. I am going to change it here itself for you to understand. Okay. So, now one more bond is being replaced by a lone pair. So, when one more bond is being replaced by a lone pair, mind it, the geometry is still tetrahedral. The geometry is still tetrahedral, but now the shape is only so much. The shape is only so much. You do not have a top atom, you do not have 3 atoms, you only have 2 atoms. We call it V-shaped. Of course, it is shaped like the letter V, correct? Or you can call it bent, or you can call it angular. You may call it angular. So, V-shaped or bent or angular. And again, the bond angle will be even lesser because now there is lone pair repulsion also to worry about. And the example that I would quote for this is H2O. And in H2O, the bond angle is 104.5 degrees. So, it is decreased even further because of lone pair repulsion. I do not mean that all the bent molecules have the same bond angle. Like for example, another thing I can quote, H2S. H2S is having a bond angle of 91 degrees. So, both are having bent shape, does not mean they have the same bond angle. Okay. So, this is AB2L2. So, once again let me remind you what all we did now. AB2 without lone pairs, that was linear with a bond angle of 180. We then went to AB3, which was trigonal planar with a bond angle of 120. We had AB2L. When a lone pair came in, the geometry remains the same, but the shape became bent, and in that for example, please remember the bond angle will decrease from 120 degrees. And then we had AB4. AB4 is having a regular geometry of tetrahedral, but then if lone pair comes in, they can change to pyramidal, or it can even become bent or V-shaped. Okay. The next molecule that we are going to try is AB5. AB5. So as you guessed, I am going to put a star because it is a regular geometry. So you have 5 bond pairs, 0 lone pair, the total is 5. The total is 5. So if you have 5 bond pairs around the central atom, see how it is being arranged. You are going to arrange 3 bond pairs in the same plane like a triangle. In the same plane like a triangle, which means the bond angle will be 120 degrees. 120 degrees. So it's like you can imagine a flat molecule with 3 bonds in the same plane. Now you have a bond perpendicular to it above that plane, and you have a bond perpendicular below the plane, which means now you have 2 types of bonds. These which are in the plane of the board or the paper, these are called the equatorial bonds. So what is the equatorial bond angle? The equatorial bond angle is 120 degrees, and these which are perpendicular to the plane, obviously 90 degree, and these are called axial bonds. Axial bonds. Axial bonds are always slightly longer than the equatorial bond. Now what is the name of this geometry? The name of this geometry is trigonal or trigonal bipyramidal. It's like you have 2 pyramids. You have one pyramid above and you have one pyramid below. So that's why the geometry of the molecule is called trigonal or trigonal bipyramidal. Okay. So this is AB5. You can quote an example of PCl5. The best example for this is PCl5 with 5 bond pairs, no lone pair. So it's a regular geometry. So regular geometry of AB5 has the geometry of trigonal bipyramidal. It has 2 types of bonds. You have equatorial bonds and you have axial bonds. The equatorial bond angle is 120 to each other, and the axial bonds are 90 degree to the plane. So I am talking about the plane in the middle. So it's 90 degree to the plane. Okay. Now this is AB5. Now let us introduce lone pairs. So I am now having 1 lone pair introduced into this. So your total is still 5, but the bond pairs are 4 and 1 lone pair. 1 lone pair. Okay. So let's see what happens. Now here I will change the structure here itself for you to understand it. So what happens here is that you are going to place the lone pair in the equatorial position. You are going to keep the lone pair because 120 degrees apart, no? So you want maximum distance. So the lone pair is placed in the equatorial position. So all of this also will get slightly bent, and this gives you a shape which resembles a seesaw. I'm sure you would have seen it in children's park and all that, like you have a board and 2 people will be on each side. So this looks like a seesaw. Look from the from a different perspective, it looks like a seesaw. So the shape is said to be seesaw, but again the geometry is still trigonal bipyramidal. Why? Because the lone pair and the bond pairs are still arranged in the form of a trigonal bipyramidal. The shape however becomes seesaw. Bond angles and all would have been distorted. So you are not going to get this exactly 90, it would have bent a little because of the lone pair and such. So this is your trigonal or trigonal bipyramidal, and you have the shape which is the seesaw shape. The example that I can give for this is SF4. The example I am saying is SF4. So sulfur is your central atom and you have 4 bond pairs, but there will be a lone pair also on sulfur, and that will occupy an equatorial position. So I repeat, the geometry is trigonal bipyramidal, but the shape has become like a seesaw, Okay. Now moving on, under the same category, I am going to give you AB3L2. So total still 5. Now you have 3 bond pairs and 2 lone pairs. Now let's see how to place it. Okay. Now when there are 2 lone pairs to be placed, I am going to place it in two of the equatorial positions. So you have one lone pair here and you have another lone pair here and you have the third bond in the equatorial position itself. So you still have your axial bonds, they won't be 90 degrees anymore, there will be a slight it will be slightly bent. Let me maybe show you that. So there will be a slight bend, there will be a slight bend and you have this. The geometry, as always, the geometry remains trigonal bipyramidal. See, it is like 3 in the same plane, one above and one below. But the shape, we are going to call it as T-shaped. T-shape. You may call it bent T-shaped also because it is not exactly perpendicular, there is a slight bend because of the lone pair repulsion. So this shape is bent T-shaped and the geometry still remains trigonal bipyramidal. None of the angles will be proper, they would have all been distorted. Okay. Now the example for this geometry or this shape is ClF3. So your chlorine has 2 lone pairs and 3 bond pairs. So when you have 2 lone pairs and 3 bond pairs, the shape of the molecule will become bent T-shaped, but the geometry remains trigonal bipyramidal. Now the last one under this category, which is AB2L3. Okay, the last one is AB2L3. Now you have 2 bond pairs and 3 lone pairs. Total still remain 5. Now you guess and tell me, where should I put the last lone pair? Obviously, I am going to put it on the equatorial position. So when I put it on the equatorial position, this here again has a lone pair. Now this is very interesting. The 3 lone pairs are symmetrical. So the axial bonds will become perfectly perpendicular. So you are going to get perfectly perpendicular axial bonds, which means now the geometry is still trigonal bipyramidal, but the shape becomes linear with the bond angle of 180 degrees. With a bond angle of it is like a straight molecule now. The lone pairs are symmetrically arranged around the central atom. So there is no bend this way or that way. It is going to be perpendicular perfectly. So that is 180 degrees. 180 degrees. And some books they say I shaped, the letter I. So that is fine as well. But simply put, it is a linear geometry, linear shape. Now the example we can see here is XeF2. So xenon belongs to group 18. It has 8 valence electrons, 3 lone pairs and 2 bonds. What will be its geometry? Trigonal bipyramidal, but its shape will be linear. What is the bond angle? 180 degrees. 180 degrees. So this concludes the category where you have total of 5. Now we have one last category and we can conclude VSEPR theory. And now the last category under VSEPR. The last category I am going to go for AB6. Yes, I will put a star because it is a regular geometry. So 6 bond pairs, 0 lone pair, the total is 6. So you have your central atom in the center. You have 4 B atoms in the same plane, and that is definitely going to be 90 degrees. You have a B atom perpendicular above and another below the plane. That is also going to be 90 degrees. The geometry is called octahedral. This geometry is called octahedral because it has 8 faces. Okay, there is like a pyramid on top, there is a 4-sided pyramid on top, as well as there is a 4-sided pyramid below. So 4 faces on the top and 4 faces below. So it is called an octahedral, or you can also call it square bipyramidal, because I said there are 2 pyramids, one on top and one below. So this is called square bipyramidal. So you may call it octahedral or you may call it square bipyramidal. This is the geometry when you have a formula of AB6. No lone pairs, only bond pairs. All the bond angles are 90 degree and there is no difference between equatorial and axial, because if you twist the molecule a little, you will notice that, like for example, if I twist it, if I consider this as the axial bond, then these 4 will become the equatorial bond. Meaning to say, in octahedral geometry, I can't can't differentiate between the axial and the equatorial bonds, they are equivalent. So you have, I will just mention all the bonds are equivalent in octahedral geometry. I am not going to specify it as axial or equatorial. All the bond angles are 90 degrees as well. So this is your octahedral or your square by pyramidal. The example for this is SF6. Sulfur belongs to group 16, 6 valence electrons, all of it has been used up for bonding with fluorine, no lone pair. So it is a regular geometry of octahedral or square bipyramidal. Okay. Now, if I introduce a lone pair, so if you have AB5L, total remains 6, but this will be 5 and this is 1. So what do I decide to do? I will take one of the positions and I will put a lone pair there. So if I put a lone pair at the axial position, for now I will say axial position, if I put it there, then what happens? Now everything will get distorted, they will all get pushed upwards, they will all get slightly pushed upwards. So the bond angles I am not going to specify anymore. And what happens to the shape? What happens to the shape? Remember, the geometry is still octahedral, but the shape now becomes square pyramidal. Why? Because now there is no pyramid on both sides. Now there is pyramid only on the top. The bottom wala pyramid is now not there because now it has been replaced by a lone pair. So the shape is called square pyramidal. The geometry remains octahedral. And the example for this is BRF5. Please note that none of the angles will be 90 degrees because all of it has been distorted by the presence of the lone pair. So that is a distorted shape and the angles are no longer 90 degrees. And we are now moving on to the last example with which we will wrap up VSEPR theory. The last example that we have is AB4L. So under AB4L2, so you are having total still 6, you have 4 bond pairs and 2 lone pairs. Very easy to understand this. Now what happens? Now this position is also going to be replaced by a lone pair. So now you have equally, like symmetrically, lone pair from top and lone pair from below. So now the distortion will not be there. The molecule will be a planar molecule with exactly 90 degrees. So the geometry is still octahedral, but I am going to call the shape as square planar because it's a planar molecule, and in this the bond angle is 90 degrees. There is no distortion because it's been symmetrically repelled from the top lone pair as well as the bottom lone pair. So the shape is become square planar, but the geometry is still octahedral, because when I say geometry, it's about how the lone pairs and the bond pairs are oriented. They are still oriented like an octahedral. So the geometry of the molecule is still octahedral, but the shape has become square planar. Now example for this, you can quote XeF4. xeF4, xenon tetrafluoride. So these are the different cases and examples for the formulae which you can discuss under VSEPR. So VSEPR theory helps us to predict the geometry and the shape of different molecules. So we had different categories, and I hope you have understood this chart. I will summarize this for you in one more simpler chart. With this we conclude VSEPR theory. Let's conclude VSEPR by doing a summary of the different formulae that we came across. The first one that we had was AB2. So AB2 did not have any lone pairs, so it is linear and the shape is also linear. The second one that we had is AB3, which is trigonal planar, and the shape also remains trigonal planar for the reason that there are no lone pairs. So if there are no lone pairs, the geometry and the shape will remain the same. Your next example is AB2L, AB12. Now the lone pair comes in. So the geometry is still trigonal planar, but the shape has become bent, and we may also call it angular or V-shaped. we may call it angular or V-shaped. Okay. Now, moving on, we had AB4. So, AB4 is tetrahedral. AB4 is tetrahedral. The geometry and the shape remains the same. If you have AB3L, as you can imagine, the lone pair will distort the geometry. So, the geometry remains tetrahedral, but the shape has become pyramidal. And the last one under that category, AB2L2, where the geometry is still tetrahedral, but the shape has become bent, or as we have written earlier, angular or V-shaped. So, these are some of the formulae. Let me continue. Now, the next formula that we have is AB5. AB5 is trigonal bipyramidal, and the shape remains the same because there are no lone pairs. So, this is also trigonal bipyramidal. So, you are having AB5 with the geometry as well as the shape, which is trigonal bipyramidal. Now, if you introduce a lone pair, the shape changes, but the geometry remains the same. Now, what happened to the shape? The shape became seesaw. The shape is now seesaw. If you have AB3L2, again geometry is still the same, the shape has become T-shaped. You may say it bent T-shaped or simply T-shaped. If you do AB2L3, so AB2L3, it becomes linear shaped, or as you say I-shaped, but the geometry remains all the same. Now, the last category, AB6. AB6, the geometry is octahedral and the shape also remains octahedral because AB6 does not have any lone pairs. The last two under this summary, so AB5L, the geometry is still octahedral, but the shape has become square pyramidal, only pyramidal, not bipyramidal, correct? So, it is square pyramidal. And the last one, which is AB4L2. So, AB4L2, the geometry remains octahedral, but the shape has now become square planar. So, these are the different categories, or if you can remember the different formulae that you need to memorize for VSEPR theory. I have made a summary chart so that it will be easy for you to remember the geometry and the shape. Make a note that whenever it is a regular geometry, meaning without lone pairs, the second column and the third column remains the same, because the geometry and shape will be the same if there are no lone pairs. It is the lone pair which will distort the geometry and therefore the shape changes. So, this is your VSEPR theory with the different examples or categories. Now, the last thing that I want to do under this session, like we have already seen the postulates of VSEPR theory, we have seen the different categories or different examples under that. Now, I will show you one very easy method how to recognize the examples. Like if I give you a random example, of course I gave you example for all of these categories, but if I give you a random example, how is it that you can figure out what is the geometry and the shape? Along with it, I will explain how to get the hybridization also. Of course, hybridization comes under valence bond theory, but I will use this method to help you recognize the hybridization also. Some few examples, some 5 or 6 examples we shall do under this. So, let me go to that situation. So, like taking a simple example, before I do the example, maybe I can set this up for you. If I want to explain hybridization, please understand hybridization does not come under VSEPR. I am just including this because it is like the same method. Okay? So, for hybridization, you can count the number of sigma bonds and electron pairs. Okay. Now you know sigma bonds means all single bonds are sigma bond. A double bond will have 1 sigma bond, a triple bond will have 1 sigma and 2 pi bonds. So you count the number of sigma bonds and any electron pairs, lone pairs. So any electron pairs that you have. If this value comes out to be 2, you can say it is sp hybridization. If it is 3, sp2. If it is 4, then it is sp3. If it comes out to be 5, then you take sp3d. If it is 6, you take it as sp3d2, and there is one more which is sp3d3. So these are the different hybridizations. Okay. Now as an example, let me take let's say PCl5. It is in our chart also, so I will take one example like that and then I will take a random example. So if I am taking PCl5, recognize the central atom. Your central atom is phosphorus. Phosphorus belongs to group 15. Now group 15 has how many valence electrons? It has 5 valence electrons. So I will put phosphorus and I will randomly put 5 dots. I will randomly put 5 dots. I do not even want to put it in any shape or anything. I will randomly put 5 dots. Now remember, chlorine is monovalent. So I will give all the 5 dots to 5 chlorine atoms, individually 1 electron to 1 chlorine atom. Now as I can see, I can write the central atom as A and I have 5 surrounding atoms without any lone pair. So this comes under the category of AB5. Look into your summary chart and tell me what is the geometry of AB5. The geometry and the shape for AB5 is trigonal bipyramidal. So without even memorizing the example, take a minute, do this. Remember the chart, of course you have to remember, but you can easily categorize your example into whichever formula that you have. So this comes under the category of AB5. So it has a geometry of trigonal bipyramidal and the shape is also the same. Now like I said, what about the hybridization? Count the number of sigma bonds and any electron pairs if it is there. I do not have any electron pairs, I have 5 sigma bonds. So what is my H value? My H value is 5. And if you get an H value of 5, what is the hybridization of the central atom? Sp3d. Sp3d. So like that, I got 3 informations based on this method. You can tell me the geometry of the molecule, you can tell me the shape of the molecule as well as hybridization by using this. Okay. Now let us confirm this concept by taking another example. Let me go for XeF4. Central atom belongs to group 18. Group 18 will have 8 valence electrons. So xenon, randomly put 8 dots. I have put 8 dots. How many am I going to give fluorine? I am going to give 4 only because I have only 4 fluorine atoms. So 1, 2, 3 and 4. Okay. Now without using for bonding, I have 2 lone pairs, right? So looking at the category, this comes under A, central atom A. There are 4 bond pairs. So I will write it as AB4 and I have 2 lone pairs, which means it comes under AB4L2. Look at your chart and you should be able to tell me that AB4L2 is having a geometry of octahedral, but the shape is square planar. You can even tell me the bond angle, because if there are no lone pairs or if it is symmetrical lone pairs, you can even tell me the bond angle. So AB4L2 is having symmetrical lone pairs. Remember all the chart that we did. So it is having symmetrical lone pair and the bond angle is 90 degrees. So XeF4 is square planar with a bond angle of 90 degrees. Now what about if we had to find out the hybridization? Tell me the hybridization in this molecule. Now for H, you need to count the sigma bonds and the lone pairs. How many sigma bonds? 4. So you have 4 sigma bonds plus, like you have to find the lone pair. So plus 2. So 4 plus 2 gives you a value of 6. And if you have 6, the hybridization is Sp3d2. Sp3d2. So the molecule is square planar with a bond angle of 90 degrees and its hybridization is Sp3d2. So this is how you can use this method to find out the shape, the geometry as well as the hybridization of different molecules. Maybe another example also. let us take an example maybe where you are having some pi bonds. Let us take an example where you have pi bonds. Let me go for, what shall we take? Okay, let us take SO2. Let me take SO2. Okay, sulfur belongs to group 16. So, how many dots shall I put? 6 dots, randomly 6 dots. Out of that 6 dots, remember oxygen is divalent. So, I will give oxygen 2 electrons each. So, I gave 2 oxygens, 2 electrons each, and I still have a lone pair, which means this comes under AB2L. A for the central atom, B for the surrounding atoms. Don't count the number of bonds, simply go for the surrounding atoms. So, AB2 and one lone pair, AB2L. Geometry is trigonal planar, but the shape is bent. I cannot say the bond angle, it varies, but yes, I can say that the geometry is trigonal planar with bent or angular or V-shaped. What about the hybridization? Let's check out the hybridization. Remember, you are supposed to count only the sigma bonds. So, in a double bond, one will be sigma and the other will be pi. So, I will not count both the bonds, I will count only one bond. So, one sigma here and another sigma here. So, I have 2 sigma bonds and I have a lone pair. So, 2 plus 1, which gives me a value of 3. So, the hybridization is Sp2. The hybridization is Sp2. So, this is how we can use this method to find out the hybridization as well as the geometry and the shape. Okay. One last one and I am going to close this session. So, this was VSEPR with an added example of hybridization. Okay. So, the last case, let me take ClF3. So that you do not have to memorize the examples, you can always get it. So, chlorine belongs to group 17, 7 dots. Okay. Out of 7 dots, 3 dots I gave to fluorine. Okay. Halogens are monovalent. So, 3 dots I gave to fluorine. So, now this is A, B, 3, L, 2. So, A, B, 3, L, 2 trigonal bipyramidal geometry, but the shape will be T-shaped. The shape will be T-shaped, correct. So, geometry is trigonal bipyramidal and the shape is T-shaped. Now, what about the hybridization? For hybridization, count the number of sigma bonds, 3, 1, 2, 3, and you have 2 lone pairs. So, the total comes out to be 5, and if the total is 5, yes, we can call it as Sp3d hybridization. Have a look here. So, Sp3d hybridization. So, this is how we can predict the geometry, shape and hybridization. I hope you could understand the class very well. Do subscribe to my PU Chemistry for more videos. Thank you.